Okay, thank you. Cool. Yes, and let me say thanks for this wonderful workshop, Christopher and Robin. All right, so spectral decomposition of the black hole Green's function. This is work with Paolo here and my PhD student, Javi Caballo. So we wrote these two papers, mostly talk about this one in October last year, and then we had another one in November. And then there's some quite closely related work by Adrian Kunz. Okay, so the object we'll be studying is the retarded bulk-to-bulk Green's function for black hole perturbations. So we're imagining scenarios in all different kinds of black hole spacetimes, so mostly stationary, symmetric black holes, something like either Schwarzschild or Schwarzschild de Sitter. So here's a piece of the Penrose diagram with a future event horizon, and this is either something like Sky Plus, or it could be, a future cosmological horizon. So in the case of Schwarzschild, asymptotically flat, Sky Plus in Schwarzschild de Sitter, with a positive cosmological constant, there would be a cosmological horizon here. And we just want to perturb these spacetimes, so we'll have some wave equation for a scalar field, or maybe some metric perturbations. And we perturb the spacetime at some location, let's say T prime and R prime, in the usual Schwarzschild-like coordinates. And we just want to look at the response. Okay, so the response is restricted, looking at the retarded Green's function. So the response is restricted to this future region. And we'll also be looking at black holes in ADS. So in ADS, of course, we have now like a time-like boundary. The boundary of ADS is here. And then we have our future event horizon. And similarly, we'll be perturbing this space-time at some time t prime and r prime, and looking at the response. Okay? So then, by causality, the response is in a region like this. So we'll only be concerned with the exterior of the black hole horizon. Okay, so precisely what is this object? It's the retarded bulk-to-bulk Green's function, which I'll denote by G, RT, T prime, R, and R prime. So given an insertion location T prime, R prime, we'll be looking at the response at some location T and R. So of course there are many transverse directions. So if we're here, we'll have a transverse S2, and here you might have a transverse S whatever, or a plane, depending on what you do in ADS. And those directions, we're just working with the decomposition of the function in those directions, so spherical harmonics or plane waves. So in the end, the equation we need to solve is the following wave equation, written in a tortoise coordinate with a potential V, depends on the radial direction, G of T, T prime, R, R prime, sourced by a delta function at this insertion location. So minus delta T minus T prime, delta R minus R prime star. Okay, so here R star is a tortoise coordinate, usual integral of 1 over f in spacetime. And we'll end up generically for whatever perturbation we're considering, scalar field or metric perturbation, all of the details of what kind of perturbation we're using, let's say species, will be inside this potential, and whatever angular quantum number L, or in the case of planar ADS, spatial momentum K will be inside this potential. So Fabian gave a nice talk this morning, and he wrote essentially the version of this in frequency space. So here we're in the time domain. All right. So why is this important? Of course, I think the retarded Green's function is a basic building block of black hole perturbation theory. If you're interested in gravitational waveforms, you have some source in the spacetime, like a plunging particle falling into the black hole. What kind of radiation does it produce? You'll want to convolve this Green's function with that plunging particle trajectory. In asymptotically ADS spacetime, usually one is more concerned with things like correlation functions in CFT, holographically dual to this. And then for things like retarded 3-point functions in the CFT, that's going to be described by some bulk computation, which at some point involves a bulk-to-bulk propagator. So these sorts of ingredients, this ingredient will appear basically anywhere you're interested in black hole perturbation theory. So we want to try and understand this object. And we want to do so not by just blindly solving this equation as we could do numerically, but we want to have a sort of spectral understanding of this object. So on a spectral, what I mean more precisely in this talk is a mode decomposition. So the mode understanding of the solution to this equation for G. So why is this even tricky? Well, if you think about an ordinary sort of problem of an idealized, let's say, piece of string with Dirichlet boundary conditions, you would then have, you would look at the fundamental modes of this string, and they would all be normal modes of the string, and then you know by some Sturm-Liouville type analysis that you could take linear superpositions of these normal modes and build a generic solution to this wave equation on a piece of string. No problem. Here, these eigenvalues of the eigenfunctions of the Hamiltonian corresponding to evolution in these spacetimes is not self-adjoint, it's not Hermitian, and as a result, the frequencies, the eigenvalues of the Hamiltonian are complex, right? These are quasi-normal modes. So here we have quasi-normal modes as eigenfunctions of some Hamiltonian. So the Hamiltonian would just be time translation. And these have complex frequencies. The Hamiltonian is not Hermitian, and we don't expect the same kind of completeness result for quasi-normal modes. So indeed, it is the case that quasi-normal modes are not complete. They are not complete. In forming a base, they do not form a basis for perturbations of black holes. And this is sort of a problem in the sense that where, in my understanding, I'm not a gravitational wave person myself, but in my understanding, by looking at gravitational wave observations, we're already starting to measure spectral properties of black holes. Right? We're looking at the ring down of these gravitational waves. People are fitting the fundamental mode, I think certainly, possibly the higher overtones, possibly the higher L's and M's, and so on. So we're really starting to measure the spectral decomposition of this, if not this object convolved with various sources. And so I think it's a good idea that we try and understand what is the spectral decomposition of this object. If it's not all quasi-normal modes, what else is it, and what's missing? Okay, so QNMs are not complete, so the basic question is what's missing? So that's what our work is trying to address.
So just what's missing, you also refer to the boundary condition, or just to this function that you would assign as a spectral one?
Let's see, so what's known is that, okay, so near I plus, in various cases it's known that if you go close enough to I plus, then QNMs are a good basis, you can represent the function. But at earlier times, this fails. And you want to know, let's say, at some early time, down here, let's say, is there some mode decomposition of the Green's function? It's not going to be QNMs, but is there something else we can use to express the Green's function as a convergent sum over some modes? So that's what we'll arrive at. All right, so what is missing? Okay, so the plan for this talk is I'll give you a bit more information about why QNMs are not complete. That's part 1. 2, what is the resolution of this in terms of these extra modes? And for this section, I'll focus on essentially black holes and ADF. They're just a little bit simpler to explain. And finally, if I have time, I'll explain how all of this works for Schwarzschild and also Schwarzschild de Sitter. So SDS, Schwarzschild de Sitter. Okay, so that's the plan. Okay, so there's actually a proof that QNMs are not complete. So this goes back, this is work by Warnick in 2022. He has some conference proceedings, I think, where he looks at the massless scalar field in Schwarzschild de Sitter. So Schwarzschild with a positive cosmological constant, essentially. And the argument is very simple. I'm just going to present the rough argument rather than any proof. So you take Schwarzschild de Sitter. So in Schwarzschild de Sitter, well, I already drew the diagram here. You have the future event horizon, you have the future cosmological horizon, and then you have some space-like boundaries. So what he says is you want to consider this wave equation in double null formulation backwards in time. So you want to start with initial, let's say, initial data for that evolution on these two horizons. So you can pick initial data, which is C infinity but compactly supported. So he has some initial data specified, let's say here and here, for this wave equation in this double null, but again backwards in time. And he uses this to evolve backwards in time to construct the solution for this scalar field. So this problem is well posed. And so what you would get on causal grounds is, a region, sort of a non-zero solution in this region. So from that, you can keep going down until you, reach whatever Cauchy surface you want, and then this gives you some initial data on that Cauchy surface, such that if you evolve it forward in time, you get solutions which are non-zero in this red region, but exactly zero in this region near I plus. Right, so the solution in this top diamond here is identically zero. So in this sense, this argument says that the support on quasi-normal nodes is nothing. There's no support at all on quasi-normal. No support on QNMs. And yet the solution is non-trivial, right? The field has a non-zero value somewhere. So this is now the proof that QNMs are not complete. After all, we have a solution with no QNMs in it, and it's a non-trivial solution. Okay, does that make sense?
Sorry, and it has no support on QNMs because it's 0 plus y plus, and there is no QNMs. So.
Exactly. So here you would think about QNMs as being an expansion near sky plus. They're exponentially decaying contributions that the work close to I plus. And here, if you looked at this solution near I plus, you would find that all the coefficients in that expansion would be 0. Okay, so this is demonstrating that QNMs are not enough. Okay, that's the first one. And then the other exercise I want to do is just to let's just start solving this equation in the standard way and see where we get to. So the standard treatment would be, say, let's Fourier transform. Okay, so we're going to Fourier transform the omega. That's in frequency space, Green's function, omega r and r prime, e to the minus I omega t minus 2 prime. So we just do the Fourier transform of this object. We plug this into our differential equation, and then of course we get an ordinary differential equation instead. So omega squared plus d r star squared minus d on g tilde is minus, and then you have a delta function only in r star. Okay. So you remove the time direction from the problem, then you've got a frequency space expression. And I'm going to focus on solving this in, as I mentioned, in ADS to begin with, just because everything is a little bit simpler to explain. And I'll explain later how it generalizes to Schwarzschild. All right. So, okay. So in ADS, we have our r star prime. Let's draw that on as some line in this geometry. R star prime. It's this location. And so we just want to solve this equation. So the first thing we're going to do is solve the homogeneous problem, right? On left, in the usual way, left of R star prime and right of R star prime, and then stitch the two things together. Okay, so the solution for G tilde is going to be conditional on whether R is less than R prime or R is greater than R prime. For R is less than R prime, we're going to want ingoing boundary conditions on this horizon, so regularity on this future event horizon. So for R less than R prime, the solution is going to be an ingoing solution. Function of R. For R greater than R prime, we're going to be over here. We're going to be looking at Dirichlet boundary conditions, in other words, normalizable boundary conditions in the context of the CFT. So this is going to be a normalizable solution, which I'll denote by n for normalizable. And then you need to, so these are the homogeneous solutions, right, on either side of this insertion. And now you just need to fix the coefficients by solving this differential equation across this join. And doing that gives you the coefficients. The coefficients are phi normalizable R prime divided by the Wronskian between these two solutions, and by ingoing of R prime divided by the Wronskian between these two solutions. So here the Wronskian is phi normalizable dr star phi ingoing minus phi ingoing dr star phi normalizable. Okay, so that's the frequency space problem solved. Right? There's no issues with that. Everyone's happy. So the remaining task, to compute the thing we want is to perform this Fourier integral. So that's where all the fun is. Okay, so to do the Fourier integral, we're going to use Cauchy. We're going to say what does this look like in the complex frequency plane. So this is G tilde. G tilde in the complex frequency plane, where are the singularities and so forth. Remember, we're doing the integral along the real axis. This integral over here along the real omega axis. So we want to deform it. Of course, if t is less than t prime, we can, well, I'll get to that in a second. Where are the singularities of this function? Well, the singularities of this function are just when the Wronskian is 0. Right? So the Wronskian is 0 is when these two solutions not independent of each other. In other words, the solution is both ingoing and normalizable, meaning we have a quasi-normal method. So these are QNMs. So these appear in this plane, somewhere down here, in this sort of Christmas tree structure, depending on what kind of perturbation you're looking at, and so on. Right, and that's all of the singularities we have in G tilde. And so if you're for t less than t prime, you're in the path of this insertion, you would close this in the upper half plane, the arc would vanish, the thing's analytic up there, and you get 0. That's the causality. And if you're not in that regime, you would close in the lower half plane. Right, so we close in the lower half plane, and so this the position space one, would then be given by sum over the residues of QNMs. We'll pick up all the residues of these Q quasi-normal modes, and plus potentially we'll have an arc contribution from the arc. Okay. In some spacetimes you'll also have a cut, and then you'll get a cut contribution. With an ADS that doesn't happen. Okay, so this is the standard approach that's due to Lever. This is Lever in 86. And this doesn't work in the sense that it works fine at at sufficiently late times. So remember all of these pieces, these residues of the QNMs, behave like e to the minus I omega m t. Right, so they decay, these frequencies of the lower half plane, so they decay exponentially with time. So if you're at late enough times, this sum is convergent, the arc goes to 0, and everything is fine. But if you're not at sufficiently late times, this sum is divergent, and the arc contribution is also divergent. We know the answer is finite, but these are both divergent in such a way that the divergences would have to cancel each other. So that's the problem. both at early times, both the QNM residue sum and the arcs diverge. All right, so that's consistent with this argument I presented, or Warnick's argument that QNMs are not complete, in the sense that when we try and represent a function using a Fourier integral as a sum over the residues of QNMs, we'll get an infinity if we're, if we're early enough times. So the key questions are really, where does, precisely where does the QNM sum fail, diverge? So where can we use a QNM sum, where can't we use a QNM sum? And again, what replaces them? So what replaces QNMs at early times?
Even if the sum converges, it might still happen that the arc gives a finite contribution or not?
Yeah, that's possible. I think it does. Well, in the examples we looked at, that doesn't happen. Yeah, that's possible.
So when you have a branch cut, you always have additional contributions.
Yeah, that's right. So here I was just, for simplicity, I focus on a DS where there's no cut. If there's a cut, of course I have a cut here as well. And yeah, so some combination of things will diverge such, and the answer will be finite, but some combination will diverge.
But
The cut, sorry, go on.
yeah, no, I just wanted to ask, like, when you're in a regime where the quasi-normal modes converge, some converges, are you okay with having an extra contribution given by the cut? Or not?
Yeah, that's fine. We think it's the same place where the QNMs work. The cut will also be finite.
So it's not really a basis, but it's still a convergent sum.
It's a convergent sum in a particular part of the spacetime, but in other parts of the spacetime, it's not.
So do you get extra contribution also when the sum converges? Or
Extra contributions from.
like,
This is no. So this is when this converges. Okay, in the examples we looked at, when this converges, this arc is 0, and this is the exact answer. It converges to the correct answer.
so it's a complete basis for large enough times.
Yes, and that's been known for a long time. You can prove it in some cases, but you need to be suitably close to I plus for that to work. So our work is only really how does this fail when you're down?
But by early times you really mean small t, or like time like. Okay.
So I'll show you precisely. Well, I'll give the answer now. We'll get to it in a second. So what happens is in the ADS case, there's different things happen in different spacetimes. In the ADS case, this is the light cone, right? What happens is the light cone bounces off the boundary. In this region, QNMs converge, and in this region they don't. And something else happens in Schwarzschild. There's an analogous thing that happens in Schwarzschild. There's no boundary, obviously, in Schwarzschild, but something like that. Yeah, so that's basically the answer to the where. Okay, so the resolution is as follows. Let's take only half of, just for simplicity, let's take half of this, right? Let's say we're at R less than R prime. All right, so we're R less than R prime. G tilde is the ingoing solution, the normalizable solution divided by the Wronskian. So I'll present this resolution. It'll seem to come from nowhere, and then I'll explain why it was working. So really, we should think about this G tilde. The argument is we should think about this G tilde as containing two distinct pieces. And the natural way you decompose it into these pieces is by recognizing that this is a local solution of the differential equation defined as an ingoing boundary condition near the horizon. This is a local solution of the differential equation defined as normalizable near the boundary. Right. Let's put them all in the same basis of solutions. So we can use a connection formula to put everything near the horizon. So we'll use Right, so second order differential equation, we need two sets of solutions to describe anything we want. And this is mixing that we can use in and out, normalizable and non-normalizable, and we're mixing things up here. So let's convert everything to in and out. So normalizable can be expressed as a sum of in and out. So these are defined at the horizon with connection coefficients, which we'll just call C normalizable in and C normalizable out. Okay. So we'll just use this connection formula, this connection to insert it into this equation. So split it up into two terms. So G tilde is now going to have a C normalizable in divided by the Wronskian. Then we'll have an in, right? So phi in, phi in, R prime, plus a second term, which is C n out divided by the Wronskian, phi in, phi out, R prime. So the Wronskian is proportional to C n normalizable out, because if you have a normalizable solution which has no component which is outgoing, then it's purely ingoing and it's a quasi-normal mode. So the zeros of this coincide with the zeros of this, and these basically cancel. Okay, there's some extra factors which I won't write down, but roughly speaking, that's what happens. And so we'll call this piece G tilde plus, and we'll call this piece G tilde minus. And now we can use these pieces to redo the Fourier integral. But now you can see that we have two terms, so we can make different choices about where we're closing the contours. And that's the key. So let's draw the complex planes for each of these. This is the complex omega plane for G plus, and the complex omega plane for G minus. Okay, so G plus still has the 1 over Wronskian in it, so it still has all of the zeros in the denominator corresponding to quasi-Moore modes. So this will have Q and N poles, as before. Q and N. Okay, here the Wronskian cancelled, so there are no Q and M's anymore. So this guy, G minus, doesn't have any quasi-Moore mode poles. So it has no Q and M. All right, but it turns out that as a result of this splitting, you've picked up new singularities in each piece, but cancel when you put them back together. So in fact, there are infinitely many more singularities in this setting along the imaginary axis in both cases, right? So we know that when we add them together, we've got to have only the Q and M's. So these singularities have got to appear with the same residues of these, but with the opposite sign, so that when we add them together, they cancel. And these correspond to the Matsubara frequencies. Of the black hole horizon, at the temperature corresponding to the Hawking temperature of this black hole horizon. So these frequencies are 2 pi I over beta n for integer n. So beta is the inverse temperature of the black hole. Okay, so now we can, as I said before, we can plug this split representation into our Fourier integral and make different choices for each term, whether we close upper or lower half plane.
So these singularities appear in the coefficients.
I'm sorry?
These are singularities of the connection coefficients.
Right, so so some of them are singularities of the connection coefficients. So this is a ratio of connection coefficients. This doesn't have any connection coefficients in it, and yet this has the same set of singularities. So these are actually singularities of the functions themselves that you normally don't see because they're cancelled by essentially the ones in the usual function. So only when you split them up do you see. I can give you some, so in the case of PTZ, then obviously solving the connection problem is simple. Everything's hypergeometric, and I can just in a moment I can point out to you precisely where each singularity comes from in the beta case. But structurally, it's the same in Schwarzschild, like in Schwarzschild de Sitter. It's the same sort of thing where the singularities come from. All right, so the picture is the one I just drew over there. We have, I'll explain what the regions are. We have our insertion, T prime, R prime. We have the light cone, we have the bounce of the light cone from the boundary, and then we have our two regions, partitioning the space-time into these two regions by this bounced light cone. So the prescription is, in region 1, you just have the ordinary Lever-style decomposition. In terms of this language, you would close both Fourier integrals to G plus and G minus in the lower half plane. Right? So it's as if you didn't split them up at all. You close this one in the lower half plane, you get the Q and M residues, you get the Matsubar residues, and here you get the Matsubar residues with opposite sign. You add them together and everything cancels, and this is just equal to a Q and M sum. So Q and M residues. So this is convergent. This sum is convergent. You can just test it with like ratio test. It's convergent in region 1. And the arc contribution vanishes in the black holes that we looked at. Okay, so in region 2, you close G plus in the upper half plane and G minus in the lower half. So G tilde plus in the upper half plane and G tilde minus in the lower half plane. Okay, so you can see that when I do that, this is the non-trivial case. You can see when I do that, you will get a sum of these Matsubaras and a sum of these Matsubaras, but because one is upper and one is lower, they no longer cancel each other. And so this is equal to a sum of a Matsubara residues. And again, this is a convergent sum. Okay, so this is essentially the problem solved. In region 1, we have a convergent sum over quasimode modes. In region 2, we have a convergent sum over these other things, which we're calling, let's say, Matsubara nodes. They exist as poles of these functions, G plus and G minus, in the frequency plane, and then they have some, the residues have some radial dependence, which we're calling Matsubara nodes. So both sets of residues, right, the Q and M residues are eigenfunctions of the Hamiltonian, and the Matsubara residues are also eigenfunctions of the Hamiltonian. It's just that we didn't consider them before because they don't obey all of the boundary conditions that you want. Right? So in the Q and M, in the usual story, you would say, what are the eigenfunctions of the Hamiltonian, which are ingoing and normalizable? The only answer is Q and M's. Here we have another eigenfunction of the Hamiltonian, the Matsubaras. They're ingoing, they are regular on this future event horizon, but they're not normalizable. But that's okay, because region 2 doesn't touch the boundary. So that's how these things are now allowed when before they were not. Yes, so the Matsubara are non-normalizable. Okay, so why these regions? I can give you a little bit of intuition about why this particular space-time decomposition works. If you just imagine you look asymptotically, well, you look near the horizon, so you look at R star goes to minus infinity, so why these regions? if I look at r star to minus infinity, then the ingoing solution behaves like e to the minus I omega r star, and the outgoing solution behaves like e to the plus I omega r star. Okay. So the combined set in the first term, so we have phi in r phi in r prime e to the minus I omega t minus t prime. So in the Fourier integrand, you also have this factor. Asymptotically, it's near the black hole horizon. This behaves like e to the minus I omega r star minus r star prime, plus r star prime plus t minus t prime. Okay, so just combining together all these wave solutions. And similarly, the d plus for the minus, you have phi in r phi out r prime e to the minus I omega t minus t prime. And that behaves like e to the minus I omega near the horizon r star minus r star prime plus t minus t prime. Okay, so you can see that these integrands behave exponentially near the horizon, and so to figure out which way you close the contour, you just need to see if this number here is positive or negative. Right, so when these change sign, when this linear combination is 0, is when you switch from one prescription to the other. Okay, so this condition here is precisely this upper line. So I drew this reflected ray here. It's this ray here. And this condition here is just a like cone. So let's call that 1, 2. This is 1. So now you can see that if you're to the future of both 1 and 2, so you're in region 1, you need to close both pieces in the lower half plane to get the exponential suppression. Whereas if you're below 1 but above 2, you need to close 1 in the lower half, 1 in the upper half plane, and 1 in the lower half plane to get the exponential suppression. So that's a reason why this works. The other thing you can do to verify these regions is, of course, just to compute the residues at large order. Let's say these Q and M residues, all these maps of error residues. You know, you stick an epsilon to the n inside here, and you look at the large order behavior of this series, and you do a ratio test. And you can show that the ratio test converges, you know, from the ratio test, you can show that it converges in the appropriate region, and not in the other region.
Can you move continuously from one region to the other and maybe some
Analytic configuration.
I mean, maybe the sum diverges, but that's something that saves you. Or, I mean, if you close
Yeah,
it,
so in the very simplest case, so if you look at very low dimensional cases, then these things are like geometric series, and this radius of convergence, you can easily analytic continue from here to here. In other cases, I think we had some hypergeometric examples. You could do the analytic continuation to all times. You can see the hypergeometric function. You can see where the singularity is. This is the singularity. You can indeed get from the Q and M sum to the Max-Barra sum. So I'm sure, yeah, I'm sure the same is true more generally. It's just that, you know, if you're in ADS4, then you would only be computing these things numerically anyway. So I'm not sure practically to do this might be tricky, but morally, exactly right.
So if the
Yes.
Matsubara modes are not normalizable,
Yes.
what gives the quantization of the frequency?
This is just okay, so the way it's not like we decided what are the modes we need to include, so let's include them. It's more, what is the analytic structure? Okay, there's these guys at integer frequencies, so that's what we include. And then you look at them, and the quantization condition then will be regularity, you know, they're the modes that fit on the thermal circle. So it's the Fourier series for the thermal circle. So it's just regularity here, essentially. And this is what this connection formula split gives you as an output. So I can't give you a better or more physical explanation of why on earth these modes are here in the Green's function, other than mathematically they're supposed to be fine. And if I wanted, let's say, you could say, how do I, knowing that this is a region which I want to construct, which modes would I use to decompose this region? I don't know how to solve that problem. Like go the inverse problem where I start with this region and I try and provide a convergent mode sum for this region. I think that's probably what you're trying to get at, right? So I don't know how to get there directly from this picture. It's more just what the singularities of these functions are telling us, if that makes sense. Yeah. Good, good. How am I doing for time? Okay. All right. So let me give you a few more. I can give you a couple of details of where these singularities come from. So in BTZ, so let's now specialize for BTZ. Well, in BTZ, the Wronskian is minus 2I omega C n out. Okay. So really I have here an I over 2 omega remaining after these terms are gone. And this is I over C n out 2 ohm. So that's the exact formula in the case of BTZ. So C n out is just some combination of gamma functions essentially. And if you look at that, that still has, this is basically the Wronskian, it still has zeros of all the Q and M, frequencies. So C n out has zeros at the Q and M frequencies, which are omega n plus minus, is plus minus m. So m is like the azimuthal quantum number on the circle, minus I, 2n plus delta. So here is a scalar field corresponding to conformal dimension delta. So these are the Q and Ms. As usual. So B to Z. This ratio of connection coefficients, so Cn in over Cn out, contains within it a ratio of gamma functions, gamma I omega over gamma of minus I omega. And this is where the Matsubara frequencies in the upper half plane come from. Right? So this upstairs gamma will have poles at I omega is minus n, where n is, a non-negative integer. So these are the upper half plane Matsubara frequencies. So here the temperature beta is, inverse temperature beta is too high. So this is the upper half plane Matsubara. Okay, so we've got the Q and M's. We've got the upper half plane Matsubaras. The next ingredient is this 1 over omega. This gives you the 0. This is the Matsubara 0. This one. And then finally, let me do this. The 1 over omega gives you the Matsubara 0. And then the remaining piece is this, these functions phi in. So phi in the BTZ case, behave like hypergeometric functions with some numbers here. And then the third argument is 1 minus I omega, some variable z. So the singularity comes from this third slot. So when 1 minus I omega goes to minus an integer, then this behaves like a gamma function, gamma of minus that integer. So that's where the lower half plane Matsubara comes from. Lower half plane Matsubara. All right, so these are poles of phi in, but we have two copies of phi in, so you get twice the multiplicity of the poles, but this also has a pole there, so you get, that reduces it back to a single multiplicity. So that's what also what happens if you don't split the Green's function up. You still have this pole in phi in, but it's cancelled by the one. So that's in just G plus, and then G minus has to follow in the same way. Like you have upper half plane Matsuvaras from phi in, and lower half plane Matsuvaras from phi out, and the 0 from the other. So that's where all this interaction is. So it seems maybe it's special to BTZ, but it's not. So if you look at Schwarzschild or Schwarzschild-de-Sitter described by Hoyne equation, you can analyze the local solutions in terms of Hoyne functions, and they have the same properties. All right, so the next thing to discuss was what about non-ADS, not asymptotic ADS black holes. Let's talk about Schwarzschild-de-Sitter first of all.
Can I ask first?
Yep.
So if I give you the data on a Cauchy slice,
Yes.
how do you decompose it?
Yeah, so I would indeed. So I would say, if you give me the in ADS. So let me just give a simplifying example. Or you mean how would I practically? Yeah. So you just take that initial data, and you'd integrate against the Green's function. So you'd have, let's say you're solving the wave equation. So you have basically the value and its first derivative on the Cauchy slice. Then there's you integrate against the Green's function and the time derivative of the Green's function, and that produces for you the field everywhere. So if as a very simplifying example, I had just a delta function source here, I would get a decomposition into regions which looks like this. And if I had now another one, let's say here, I would get a second decomposition of that perturbation into regions here. So now you see that I have in let's say this region and union this one, I have only QNMs. In these regions, I have only Matsubara frequencies. And in this third region, you have a mixture of both QNMs and Matsubaras. So you can see that as you move this point, so if I had some compactly supported data instead of these 2 points, it just changes it slightly, doesn't do much. If I move this point closer and closer to the horizon, this region here gets smaller and smaller. Essentially, you'll end up with a space-time which has no QNM decomposition at all. Everything is either mixed or purely Matsubar. Okay, so let's talk about Schwarzschild-de-Sitter. So this is a lambda positive scenario. In Schwarzschild-de-Sitter, there's no time-like boundary for this reflection to happen from, but it still happens. So in Schwarzschild-de-Sitter, there are 2 cases. There's a piece of the Penrose diagram for Schwarzschild-de-Sitter. Turns out there's a very special location, which we'll call our bounce. You can compute this location, our bounce. I don't know physically what it corresponds to. It's not the peak of the potential. It's not the light ring. It's just some location in the space-time, but it's somewhere you can compute. And if R prime, your insertion is less than R bounce, then the decomposition happens in this way. You get the light ray coming off, and it bounces off this R bounce. So you get a region 1 and a region 2. And if R prime is to the right of R bounce, then the opposite thing happens. You get the bounce from this location here. Region 1 and region 2. So again, region 1 is QNMs. And region 2 is the Matsubara region. So which Matsubara frequencies, right? So now we have Schwarzschild-de-Sitter. It has 2 horizons with 2 different temperatures. So this one has Matsubaras at beta corresponding to the black hole temperature. And this one has Matsubara decomposition at beta corresponding to the cosmological horizon temperature.
The quasi-normal modes, they see both temperatures.
So the quasi-normal modes, they're just what they are, I guess. They're split into two families, typically, right? So if lambda is small enough, let me just draw the complex plane for G tilde, not the split one, right? So just phi in, phi up, divided by the Wronski. Then, as long as lambda is not too large, then you can morally split them, the quasi-normal modes, into things that look like the quasi-normal modes of the black hole, and things which look like the quasi-normal modes of the pseudo-static patch without a black hole. So these live on the imaginary axis. And these are spaced by basically the square root of lambda. These on-axis nodes. So region 1 contains all of them, both the de Sitter modes and the black hole modes. So if you have the space-time looks like this, you perturb a black hole, and the black hole perturbation is far enough away from the black hole that you're to the right of this bouncing line, then if you're an observer in this space-time, like an asymptotic observer, of course, like the waveform you measure will be first described by the sum of Matsubaras, and then there'll be this critical value of time, after which you'll get a convergent sum of the QNMs. So if you're measuring your signal as an asymptotic observer, and you try and fit it to QNMs, at these times here, you will fail. It won't converge. You instead have to use this Matsubara frequencies to do it. And you can check this, and it works very well. To reproduce, you can check it against the numerical integration of the PDE that I wrote down at the beginning, and you can check that the Matsubara sum converges to that solution here and only here. If you try and use it here, it will fail. The QNM sum converges to that solution here and only here. If you try and use it here, it will fail. Okay. All right, so the final thing I wanted to talk about was the limit as lambda goes to 0. Right? So this is Schwarzschild de Sitter. Maybe if you're more interested in gravitational waves, okay, we live in a universe with a very small cosmological constant, but let's forget that and say lambda goes to 0. So we replace this cosmological horizon with Spectral plus, basically. Then what we're proposing is that you can get there directly from this picture, or from this finite lambda picture, by taking lambda to 0, you compute the results here, and then you take the lambda to 0 limit of those results, and you'll get the right answer. So what do I mean by that? What I mean is that, okay, these quasi-normal modes on the imaginary axis are spaced by, so I'm talking about region 1 now with QNMs, so I don't need to split the Green's function up. So QNMs on the imaginary axis spaced by the square root of lambda. So as lambda goes to 0, these get closer and closer together and closer to the origin. So as lambda goes to 0, we'll get a complex plane which has QNMs in it, and these coalesce into a cut. This is the usual cut that you get in Schwarzschild. So the branch point here, and usually you draw the cut this way. So what we showed in this other paper that I mentioned at the beginning, so Paolo and I, is that if you take the residue sum of all of these de Sitter modes on the axis, in the limit lambda goes to 0, this reproduces for you precisely the discontinuing integral of the cut. So this price law tail that comes from the cut, you can represent it as a sum of quasi-normal modes as long as lambda is small enough. Okay, so that's for region 1, the quasi-normal mode region. In region 2, something similar happens. Well, depending on which region 2 we're talking about. If we're in region 2, this region 2, so if our perturbation is less than our bounce, then these are the Matsubara frequencies of the black hole. And so as lambda goes to 0, these don't do much at all, they just stay put, they're well separated. But over here, these are the Matsubara frequencies for the cosmological horizon, so as lambda goes to 0, these will also come together, like the QNMs do. Right, so in region 2, say, let's look at G minus. G minus, remember, has only the Matsubaras. And these are spaced, again, by the square root of lambda. And as you send lambda to 0, these will form a cut of some kind. So now this is not the same cut that you get for Price's law, right? So this cut here is just in the full Green's function. These cuts only exist in the split of the Green's function into two pieces. And this you can call, I don't know, let's say Matsubara cut. This is a different contribution. Indeed, so if you did the sum over the residues of these Matsubara modes, this will reproduce now the discontinuity integral of this cut. All right. Okay, so that basically brings me to the end. So let me summarize. Okay, so I think this, given the increasing level to which we can measure gravitational perturbations with gravitational waves and so on, I think a spectral decomposition is increasingly important. So we started with the most basic observable, which is the Vitali-Green's function. This usual lever 86 type spectral decomposition fails at early times, and that's because essentially quasi-normal modes are not complete. And so early times you need something else. That something else are these Matsubara modes, and this is a completeness result. So for any global completeness result. So anywhere in the space-time after you perturb it, I can give you a convergent mode sum for the Vitali-Green's function. And yeah, that's it. Okay, thank you.
Thanks for the talk. Question?
When I am on the line between 1 and 2 equations,
Good question.
yes,
I'm not entirely sure. Hopefully at least one of those two representations converges, but we're not.
In the Posteller case, both were okay. We
Yeah,
tested it
Posteller.
analytically.
Yeah.
But yeah, for Schwarzschild de Sitter, it was more complicated because it seems that you really had some singularity structure that for Posteller was not the case. So for Posteller, you got some singularity on this same complex radius of convergence, basically, but was not this real location. For Schwarzschild de Sitter, it seems actually to be the real location, so both sums seem to be problematic from both sides.
Yeah, so that's it's very interesting because of course when you want to do like gravitational wave or whatever kind of calculation, you're going to want to start convolving this thing against the source, and then this boundary between the two regions is going to be dragged across the whole space now. So that has its own type of contribution. Then one would need to address that. But right now we're just hoping that everything is like one of the two will converge there. And, yeah, but we're not sure yet.
Friends. So if I was interested in computing scaling amplitudes, I have to take limit of which the solutions of the equations at r constant,
Yes,
right?
yes.
So does the flat space limit commute with the r to infinity limit? What?
You mean the lambda to 0 with r
Yeah,
star?
yeah.
Okay. So what we found is that if you work with, what do you keep fixed while you do this, right? So we found if we work with r star and take lambda to 0, then everything seems to go through from one case to the other. If you fix r, it's obviously terrible because r is what r does near the cosmological horizon is nothing special. But r star. This is r star to infinity. This line here, right? It's r star to infinity. No matter what, whether lambda is 0 or non-zero. So if we work with fixed r star, then everything seems okay. There is this issue that the analytic structure of these G plus and G minus change. So remember this result that the S matrix doesn't have the same analytic structure as the Vitali-Green's function. And so indeed that happens here too. Like many of I think some of the, like half of the Matsubaras are gone. Like one of the either up or lower, I don't remember. And, but that's fine. You can check that the residues of the remaining half do produce the result, the correct result. So it's like the residues are vanishing as you take r star to infinity. So I think everything does go through the there's no obstacle to doing this, is what I think. Like the analytic structure changes, but only because residues vanish. That would be my statement.
So in the middle part of the black hole, you explain the case where you have two sources, and so in the case when you have infinitely many sources on the Cauchy slice, what would be the situation?
So indeed, so if you had some, so this would be this diagram here, right, would be the case where on this Cauchy slice, the only the region of support of the initial data is just these 2 points.
Yeah.
But you could imagine filling the whole Cauchy slice up with support everywhere. Just pick some arbitrary initial data, and then the question was, how does this decompose? And I think it decomposes. Generically, the answer is you have to consider a mix of both types of modes, the Matsubara modes and the Coisinot modes. If you do that, you should be able to describe the response to arbitrary initial data as a sum of a convergent sum of both sets of modes.
Is there an inner product that allows you to project in these modes?
So, so for quasi-normal modes, there's a product, I wouldn't call it, like, it's not a well-defined norm or an inner product. So Paolo and I, again, also with Javi, had some work, in the ADS case, we have some work building, it's a bilinear. So instead of being anti-linear and linear, it's bilinear. It's linear in both slots. And we can build, this thing where if you put a quasi-normal mode in one slot and a quasi-normal mode in the other slot, the answer is delta Mn. Right, we could build this thing. This thing involves taking like the Klein coordinate in a product, but on a complex contour. It's sort of like a contour that connects one. So here there's some two-sided picture, and this contour connects basically one side to the other. And it's not a normal. You need this complex integration contour, and you need linearity, whereas normally you would have antilinearity in this slot, and then you could make it work. This is very similar to constructions by Stephen Green and collaborators for Schwarzschild and Kerr.
But that one was only for Cosinor modes.
For Cosmos, yes, indeed. So for the Matsubara's, yeah, we haven't considered. I think it should be possible to extend. I think you have to change the contour a little bit. Like you have to. So this basically goes round half a circle. You have to go around a little bit more, I think. And then you could include. You should be able to include Matsubara's in the construction like this. I think, yeah, it should be possible, but we haven't done it. Yeah. Thanks.
Any questions?
If you have care, does it changing a lot?
Care. I don't. Yeah, the answer is I don't know. Yeah. No, I can't think of anything intelligent to say about Kerr. I mean, yeah, the only spacetimes we analysed were Posh-Teller model, black holes in ADS, Schwarzschild de Sitter, and this flat limit. We haven't done any rotation, but I'm sure one could try and do this similar set of things. But I guess, yeah, I mean, this procedure was about converting everything in the Green's function to local solutions at one end, one regular singular point with differential equations. So you have to look at Kerr and see what are the appropriate singular points and connect them. And I think this should be something.
I think it should work, right? It's just that the similarities are the same, right?
Okay.
Yeah, I think you will
The
have
only
some
thing that you have to
changes
worry
also in the
is,
Matsubara mod. Yeah.
maybe it's like a radian frequency that you have to worry about.
Yeah, I think
Is this upper Matsubara mode is connected to the Aretakis instability?
well, nothing here is extremal. So even let's say in can say, our attack is occurring in ADS. Sure. Anyway, so in ADS, let's say this would just be Schwarzschild ADS with a final temperature, as I don't think there's any Artakis business going on. And here you could focus on this region close to the black hole horizon, and again, it's not extremal in any sense. I mean, in a way, like null infinity is the extremal limit of Schwarzschild de Sitter as lambda goes to 0, but that's only for this particular setup. Like you still get the upper half plane that's of ours here, and this is just a finite temperature horizon. So not off the top of my head, I wouldn't draw a connection between the two things. Might be interesting to think about.
More question? Okay, then let's thank the speaker again. We have a coffee break up.